Welcome to all. We will start today's class. So I will discuss a new topic today, electric dipole. Di means two, pole means polarity, charges. Okay. So an electric dipole means it is a system of two equal and opposite charges separated by a small distance. So, what is an electric dipole? It is a system of two equal and opposite charges separated by a very small distance. Distance between the charges is very small, in millimeters or less. Okay. If the distance between the charges becomes smaller, approaches to zero, it is not zero, approaches to zero, then the dipole become ideal. Okay. So we can see these dipoles in different molecules, different substance. So what is an electric dipole? It is a system of two equal and opposite charges separated by a small vector distance. And now I am introducing a new quantity called a dipole moment. Dipole moment. See, if you multiply the product of either of the charge and distance between them, we get a quantity called a electric dipole moment. So what is electric dipole moment? It is a product of magnitude of either charge and the distance between the dipoles. Distance between the charges. Okay. The distance between the charges is known as dipole length. Okay, we usually denote it by the letter 2A or 2L. So what is an electric dipole? It is a system of two equal and opposite charges separated by a small distance. I will write here electric dipole. It is a system of two equal and opposite charges separated by a small distance. So we have to consider two charges. This is positive charge, negative charge, identical charges, separated by a small distance. This distance between the charges we take as 2A or 2L. This distance is known as dipole length, distance between the two charges. We denoted by 2A. So we can consider the center of the system O. So one charge to the center distance is A. Now, electric dipole moment. What is the electric dipole moment? It is the product of magnitude of either charge and the distance between them. Distance between the charges is known as dipole length. Dipole moment we denote by the letter P. Dipole moment. We use the symbol P. What is it? It is defined as the product of magnitude of either charge and the distance between the charges. So the equation is P equals Q into 2A. 2A is known as dipole length. This dipole moment is a vector quantity. It has direction. Direction of dipole moment is from negative charge to the positive charge. So remember, direction of dipole moment is from the negative charge to positive charge. Direction of, remember, what is the direction of dipole moment? It is from negative charge to positive charge. So, dear students, what we learned so far, we learned what is an electric dipole. An electric dipole is a system of two equal and opposite charges separated by a small distance. Now we learned another quantity, dipole moment. It is a product of magnitude of either charges and the distance between them. Dipole moment is a vector quantity. What is the direction of a dipole moment? It is from negative charge to positive charge. What is the equation for dipole moment? Q into 2A. Now, what could be the SI unit of dipole moment? You know, dipole moment is charge into 2A. You know the unit of charge and unit of distance. So, SI unit of dipole moment is Coulomb meter. Coulomb meter. SI unit of electric dipole moment is Coulomb meter. Now we will discuss if we place an electric dipole in a uniform electric field, what will be the effect of the field on it? Okay, so we will see that the dipole will be rotating. Okay, or there will be a torque. The rotating effect is known as torque. There will be a torque acting on the dipole. So we will discuss it. So our next topic is torque acting on an electric dipole placed in an electric field, in a uniform electric field. Torque acting on an electric dipole placed in a uniform electric field. So first we have to draw the diagram. See, You know how to represent a uniform electric field. A uniform electric field is, we can represent by parallel equidistant straight lines. See, I am drawing here a uniform electric field. So I have to draw parallel equidistant lines. The arrow mark shows the direction of the electric field. So this is a uniform electric field. Now I am placing an electric dipole. An electric dipole I am keeping at an angle with the electric field. Okay, so I am drawing the electric dipole. This is negative charge, positive charge. Okay, it is length. The length of the dipole is 2a. This charge minus q. Positive charge plus q. And you know, if you keep a charge in an electric field, it will experience a force. The force will be in the direction of the electric field. Okay, so we are considering as a derivation, you have to explain the terms first. Let q be the charge, 2a length of the dipole. Okay, so there are two charges here. The positive charge q experiences a force due to electric field. It is along the field direction. You know the equation for electric field. What is the equation? E is equal to F by Q. So what is the force on the positive charge? Force will be Q into E. So force acting on positive charge. What is that? Q into E. We use the equation, we learned electric field is F by Q. It will be along the positive x direction. See, force, this force will be along the positive x direction. This is QE. The negative charge, since charge is negative, it will experience a force opposite to the previous force. It will be along minus x direction. It is minus QE, right? So force acting on minus q, it is minus QE. Okay, see, if I write the direction, plus QE is along I direction, I hat, minus QE is along minus I hat, right? So what is the total force acting on it? When you add these two forces, we will get 0. Total force acting on the dipole. Force, you add it, minus QE I hat plus QE I hat, it is 0. So we saw that if an electric dipole is placed in a uniform electric field, there is no translatory force acting on it. Total force on it is 0. But remember, if the dipole placed in a non-uniform electric field, there will be a force, because there will be a net force, because all these forces on individual charges will not be equal in magnitude. So there will be a net force. So remember, when an electric dipole is placed in a uniform electric field, no translatory force act on it. Total force on it is 0. But if the field is non-uniform, there will be a net force. Remember this point. Okay. So when an electric dipole is placed in a uniform electric field, we saw that no external, no translatory force act on it. But you can see these two forces are equal, opposite, but their line of actions are not the same. They have different lines of action. They act along different lines parallel to each other. Okay. But as a result, there will be a torque. So when an electric dipole is placed in a uniform electric field, net force on it will be zero, but it will tend to rotate. There will be a torque acting on the dipole. This torque tends to align the dipole along the field direction. Okay, this torque tend to align the dipole along the field direction. If you keep the dipole in this direction, if electric field is along x direction, okay, there will be a torque. If you release it, the dipole become parallel. It will align along the field direction. So what is the effect of this torque? The torque acting on the dipole tends to align the dipole along the field direction. Okay. These two forces are equal and opposite, but their lines of actions are different. But their lines of actions. So what will happen? The dipole will experience a torque. If the lines of action are along the same point, force will be, torque will be zero. But here lines of actions are different. So there will be a torque. What is the effect of this torque? This torque tends the dipole to align along the direction of the electric field. Tends to align the dipole along the direction of electric field. Okay. Now we can obtain the magnitude of the torque. You know the formula to find out the magnitude of torque. Simple formula, force into perpendicular distance. So in the diagram, say the dipole moment make an angle theta with the direction of the electric field. This angle is theta. So how you can find out the torque? Torque is magnitude of either force multiplied by the perpendicular distance between the forces. You know the two forces, minus QE and plus QE. What is the perpendicular distance between them? I am giving the name charge minus Q as A, charge plus Q as B. So perpendicular distance between these two forces is, see, I have drawn there, I mark it as this point, perpendicular as C. So BC is the perpendicular distance. From the figure, see the triangle. Did you see the distance BC? BC is the perpendicular distance between the two forces. Now you can calculate torque. You know how to calculate torque. What is the equation? Magnitude of either force into perpendicular distance between the forces. So, torque acting on the dipole. What is the equation? Either force into perpendicular distance between the forces. Okay. You know the magnitude of either force, QE. So in the next line, instead of either force, QE into perpendicular distance. From the diagram, what is that perpendicular distance? Perpendicular distance is BC. So into BC. Now you look into the diagram, you can find out BC in terms of the angle. See, from the triangle ACB, what is sine theta? Sine theta equals opposite side of the triangle BC by AB. So BC by AB is 2A. So what is BC? 2A sine theta. BC is 2A sine theta. So you can put it in the equation. Is equal to Q into E into what is BC there? 2A sine theta. This I write as Q into, I am writing 2A first, into E into sine theta. And you learned Q into 2A. What is Q into 2A? Electric dipole moment. But Q into 2A equals P, electric dipole moment. So we can write the equation for torque. What is the symbol for torque? You know the Greek letter tau. This is torque is equal to, instead of Q into 2A, P into E into sine theta. So this is the equation for the magnitude of the torque. Okay, this is the equation for the magnitude of the torque. We have to express in vector form. Torque, it is a vector quantity. What is its unit? Torque is force into distance only. So it is Newton meter. So it is a vector quantity. So we have to express in vector form. In vector form, we can write tau bar equals P bar cross E bar. You know, A cross B is AB sine theta. So torque acting on the dipole placed in a uniform electric field is tau bar equals P bar cross E bar. P cross E. And what will be the direction? Vector product direction, you know, right hand thumb rule. The torque will be perpendicular to P and E. Torque will be perpendicular to P bar. Torque will be perpendicular to E bar also. P and E bar may not be always perpendicular, but torque is always perpendicular to P bar and E bar. So what are the two pairs of vectors perpendicular to torque here? One is dipole moment, other is electric field. Okay, torque is perpendicular to P bar and E bar. Torque is perpendicular to P bar and E bar. So the two pairs of vectors perpendicular to torque is, one is dipole moment and torque, other is electric field and torque. Okay. So what are the key points in it so far? First one is, when an electric dipole is placed in a uniform electric field, it will experience a torque. Okay, but it will experience no torque, no net force. If the dipole is placed in a non-uniform electric field, it will experience with both torque and both force. Now we can discuss some special cases. Case 1. What is the first case? If theta is 90 degree, if the dipole is placed perpendicular to the magnetic field, theta 90 degree. So what will be torque? Torque equals P sine 90 is equal to P into E. In this case, torque will be maximum. You know, sine value. Sine has maximum value when angle is 90 degree. This I am writing tau max. Case 2. Theta is 0 degree or 180 degree. What will happen? 180 degree. Sine 0 or sine 180. It is 0, you know. So torque will be 0. So when dipole is placed parallel to the electric field or anti-parallel to the electric field, torque acting on it is 0. In the first case, electric field and dipole were parallel. Electric field, dipole, parallel. Sorry, first case they were perpendicular. So when dipole is placed perpendicular to the electric field, maximum torque. Second case, electric field and dipole moment are parallel or anti-parallel. Then torque is 0. One more case we will discuss. If theta is 30 degree, if the electric field make 30 degree with the dipole length, then tau is equal to P sine 30. Sine 30 value is 1 by 2. P into 1 by 2. So it is half of maximum torque. Okay. So when an electric dipole is placed in a uniform electric field, will it experience any force? No, it will not experience a net force. But what will happen? What will it experience? It will experience a torque. What is the effect of that torque? This torque tends to rotate the dipole to align it along the field direction. Okay. If dipole is placed in a non-uniform electric field, it will experience a net force and a net torque. Remember. When will be the torque maximum? When the dipole is perpendicular to the electric field, torque acting on it will be maximum. When will be the torque zero or minimum? When the dipole is placed parallel or anti-parallel to the electric field, the torque will be minimum or zero. What is the equation for torque? Tau equals, in vector form, tau bar equals P cross E. What are the pairs of perpendicular vectors? One is tau bar and P bar, and tau bar and E bar. Now we will go to the next topic. See, we have seen when a dipole is kept at an angle in a uniform electric field, it will experience a torque. If you release the dipole, it will go back to the field direction, align along the field direction. If we want to rotate the dipole against this, so suppose dipole was initially parallel to the electric, torque on it will be zero. If you want to rotate it, you need to do a work. So when you do work, you have to spend energy, right? So this work done to rotate the dipole is stored in it in the form of electrostatic potential energy. Electric potential energy. So next we are going to find out the equation for the potential energy of a dipole in a uniform electric field. So when a dipole is placed along the field direction, torque acting on it zero. If you want to rotate it against the field direction, you need to do work. This work done is stored as the electrostatic potential energy of the system. So now a small derivation, we are going to derive the equation for the electrostatic potential energy of a dipole. So I am writing the next heading, potential energy, potential energy of an electric dipole. In a uniform electric field. So I represent a uniform electric field. This is the uniform electric field, E. Okay. So what is E? Strength of the uniform electric field. And I am placing a dipole. See, this is the dipole. Minus Q charge plus Q charge. Q charge of the dipole. And 2A is the length. You know the notation, 2A, length of the dipole. 2A is the length of the dipole. The dipole make an angle theta with the field direction. Theta, angle between dipole moment and electric field. See, these are the assumptions for the derivation. So you first write let and write these assumptions for derivations. It is important. Okay. Otherwise, you may lose half mark if you don't write the symbols like this for the derivation. Now, suppose I am rotating this dipole through a small angle against the electric field, small angle d theta, and I am finding the work done. So what is the work for equation for the work done in rotational dynamics? Tau d theta, torque into angular displacement. So the small amount of work needed to rotate the dipole against the field direction is, we can represent it as dw. What is the equation for torque in rotational dynamics? Tau into d theta. And we already know the equation for torque. Okay. Torque equation is torque equals P sine theta. So what is the equation for work done? P sine theta d theta. So this is a small amount of work done to produce a small angular displacement. Now, how will you calculate the total work done? You have to integrate this. Always for finding total work done, you integrate it. Therefore, total work done W equals integral P sine theta d theta. Suppose initially the dipole was making an angle theta 1. See, this angle is theta 1. Okay. And I rotated it through an angle theta 2. So final angle. So this is the final position. This angle is theta 2. So we are rotating from the angle theta 1. Initial angle with the field was theta 1 to a final angle theta 2. So what will be the work done? Then you have to put the limits for integration. Okay. So work done to rotate the dipole from angle theta 1 to theta 2. W equals, you have to put the limits, integral theta 1 to theta 2 P sine theta. P and E are constant for a given dipole. Integral theta 1 to theta 2 sine theta d theta. And you know the standard result, integral sine theta d theta is minus cos theta. But integral sine theta d theta is minus cos theta. Therefore, work done is what? Minus P this minus cos theta, but you have to write the limits on the right hand side of the square bracket, theta 1 to theta 2. Next step is you have to apply the limits. How to apply limits? First you apply upper limit, then minus lower limit. So W is equal to minus P cos theta 2 minus cos theta 1. This work done is stored in the dipole as its potential energy. This work done is stored as potential energy. So what is the equation for potential energy? I usually write the symbol U. U equals minus P into cos theta 2 minus cos theta 1. This is the equation for the potential energy of an electric dipole in an external field, placed in an external field. Students, I believe it is clear to you. Now we can discuss some special cases. First one, if theta 1 is 90 degree, theta 1 90 degree, initially the dipole was perpendicular, then torque will be maximum, right? And theta 2 is 0. Then what will be the work done? Potential energy minus P cos theta 2 0 minus cos 90. It will be minus P only, because cos 0 is 1, cos 90 is 0. Okay. Second case, if theta 1 is 0 degree, initially dipole was along the field direction. Theta 2 is 180 degree. Then what will be U? Minus P into theta 1, theta 2 cos 180 minus cos 0. This will be minus P into minus 1 is equal to 2P. Theta 1 0, theta 2 180 degree, potential energy is 2P. Third case, if theta 2 is 90 degree, theta 1 is theta. Sorry, theta 1 is 90 degree and theta 2 is theta. What will be the potential energy? U is equal to minus P cos theta minus cos 90. So you are getting minus P cos theta. So this you can write as minus P dot E. So these are the different cases. Now here, if you consider two sub cases, in this, if theta is 0 degree, then what is U? Minus P. Okay. If theta is 0, that means here theta 2 is 0, theta 1 is 90 degree. So U is minus P. So here the dipole is parallel to the electric field. When the dipole is parallel to the electric field. Potential energy is minus P. You can see potential energy is negative. It is in stable equilibrium. Dipole is in stable equilibrium. So if the dipole is making an angle zero or it is parallel to the electric field, the dipole will be in stable equilibrium. If theta is 180 degree, what will be the potential energy? Minus P into cos 180 is minus P into minus 1 P. So potential energy is positive. Now the dipole is said to be in unstable equilibrium. So when the dipole is placed parallel to the electric field, potential energy in it will be minimum. It has minus P. The dipole will be in stable equilibrium. Okay. If dipole is placed 180 degree with the electric field, it will be in unstable equilibrium. Energy is maximum. You know, when energy become maximum for any object, it become unstable, right? What is the difference between stable and unstable equilibrium? See, suppose dipole is in stable equilibrium. If you try to displace and leave your hand, it will stay there only. Okay. Unstable equilibrium means if you tends to displace and leave your hand, it will go back. Then it is in unstable equilibrium. Okay. So dear students, today's class we will stop. We will see in the next class. Children, watch the videos repeatedly, learn yourself, like and subscribe. Thank you. Thank you for all.